Hello everyone, I am Lokesh, working as an assistant professor in Department of Physics at Maharaja Institute of Technology, Mysore. Today, in this video session, I am going to discuss about the basics of forced oscillation, the expression for the amplitude and phase of the forced oscillation, and the cases relating to the forced oscillation. Now, let us see what is meant by forced oscillations. Now, if you consider any oscillations, or in the case of harmonic oscillations, the frequency of the oscillation goes on decreases exponentially with the time. Now, this is because of the presence of the damping factor, which is because of the medium. For example, the frictional forces which are acting on the oscillations like air and other forces which are acting on the oscillating body, because of these other forces, the oscillation of the body goes on decreases exponentially. Now, if you want the oscillating body to continuously oscillate, what we have to do is we have to give an external force to the oscillating body with the energy such that the amplitude of the oscillating body does not decrease exponentially with the time. So, such kind of oscillations wherein we give an external force so that the amplitude of the oscillation does not decrease exponentially with time are called forced oscillations. The oscillations in which an external force is applied on an oscillating body in order to make it oscillate continuously are called forced oscillations. Now, in the case of forced oscillations, what we do is we give an external force of the same frequency and same amplitude which we have applied earlier to an oscillating body. We apply the force again so that the oscillating body does not stop exponentially with the time. So, that kind of oscillations we call as a forced oscillations. Now, some examples for forced oscillations are oscillations of swing, then oscillations in tuning fork, now based on this forced oscillation definition, next what we are going to do is we are going to derive an expression for the amplitude as well as the phase of the forced oscillations. Or let us consider a simple pendulum. Now, in the case of simple pendulum, what we will do? So, let us consider a simple pendulum. Let it be at the equilibrium position. Okay. Now, our work is done in order to bring the simple pendulum to the extreme position, so that it starts oscillating. So, as soon as we give the force to the simple pendulum starts oscillating. Now, what we have to do is we have to make this simple pendulum oscillate continuously so that it does not stop. So, that is the basics of what is meant by forced oscillation. So, there are three forces acting on the oscillating body for the forced oscillation. One is the restoring force acting in the opposite direction of applied force is given by is minus k into y. We'll call this as equation 1. The frictional or damping forces acting in opposite direction to the velocity of oscillating body is given by minus r into dy by dt. This is the second force. The first one is the force, the restoring force acting in the opposite direction to the applied force is given by its minus k into y. Minus sign indicates that the force is acting in the opposite direction. Again, the frictional forces or the damping forces acting in the opposite direction to the velocity of the oscillating body, it is given by minus r into dy by dt. Now, we have the third force which is making the body to oscillate continuously without decreasing the amplitude of the oscillating body. The external force applied on the oscillating body given by F sin Pt. We'll call this as the total forces acting on the oscillating body is given by, so we'll set equal to, now we have the first force, that is it's minus k into y. The second force, we have the second force, that is minus r into dy by dt. Now the third force is the F sin Pt, where F is the amplitude of the applied force and P is the angular frequency of the applied force. Okay. Because of that, we have to add this term F sin Pt to the equation. So we'll call this as equation. The force applied is equal to its mass times acceleration due to gravity. So what we have to do is we have to convert this expression in the differential form. So we know that the force applied can be written as mass times, if the acceleration can be written in the differential form as d square y by dt square. So we'll call this as F1 and call this as F2. So we'll call this as, so comparing equation 4 and equation 5, m into d square y by dt square is equal to minus k into y minus r into dy by dt plus f sin 6. Now again this has to be arranged in order to get the differential form of this equation. So, basically this equation will become a second order differential equation. So, we have to keep the equation or rearrange the equation in the second order differential equation form. So, we will divide equation 6 by m, then we will get its d square y by dt square is equal to minus k by m into y minus r by m times dy by dt plus f by m times sin pt. We have to bring this to a second order differential equation form, so we will just rearrange it. So, this equation becomes d square y by dt square plus r by m into dy by dt plus k by m into y is equal to f by m sin pt. We will call this as. So, let the solution for the equation 7 is given by y is equal to a sin pt minus theta. We will call this as equation 8. Now, since we have assumed the equation or the solution for the equation as y is equal to a sin pt minus theta, so what we have to do is we have to find out the amplitude as well as the phase difference for this differential equation. So, in order to find out the amplitude as well as the phase difference for this differential equation of forced oscillation, so we have to go on differentiating the equation 8, so that I can substitute those values here in this differential equation of the forced oscillation, and later we will be able to find out the solution. So, we will differentiate equation 8 with respect to t. So, it is dy by dt is equal to, we have to differentiate the equation 8 in order to obtain the amplitude as well as the phase of the forced oscillation. So, if we differentiate the equation 8, so we get dy by dt is ap cos pt minus theta, and if we differentiate further, so it is minus ap square sin pt minus theta. We will call this as 9, we will call this as 7. So, we have equation 7 as d square y by dt square plus r by m into dy by dt plus k by m into y is equal to f by m sin. Now, in order to simplify this differential equation further, what we will do is we will substitute r by m is equal to 2b, k by m as omega square, and f by m as capital F. So, this differential equation becomes d square y by dt square plus 2b into dy by dt plus omega square y is equal to capital F sin pt. So, to this differential equation we will substitute the values of 8, 9 and 10. So, the differential equation becomes, so this is minus ap square sin pt minus theta plus 2b into AP cos Pt minus theta plus omega square A sin Pt minus theta is equal to f sin Pt. We will call this as equation A sin Pt minus theta. So, we are left with omega square 1 and it is minus p square plus 2b AP cos Pt minus theta is equal to f sin Pt. We call this as equation 12. We have to substitute certain terms to the equation 12 in order to simplify this equation further. We have to substitute the values in such a way that the value or the value of this whole equation does not change, so that we will be able to find out the amplitude as well as the phase difference for the forced oscillation. So, we can write this as f sin Pt minus theta, then plus theta okay. So, as you can see, I have added theta and subtracted theta, so that the equation does not get changed. So, we will just write this A sin Pt minus theta omega square minus p square plus 2b AP cos Pt minus theta, and then we added and subtracted theta to the right hand side of the equation. So, we will call this as equation 13. Now, using equation 13, what we have to do is we have to simplify the equation 13 further, so that we will be able to get the amplitude as well as the phase of the forced oscillation. Can be written as this is f sin Pt minus theta plus theta. Now, as if you see this is in the form of sin of A plus B. So, we can expand in the form of, we will just write the whole equation. A sin Pt minus theta into omega square minus p square plus 2b AP cos Pt minus theta is equal to, we will expand it f into in the form of sin of A plus B sin Pt minus theta into cos theta plus cos Pt minus theta into sin theta. Comparing coefficients of sin Pt minus theta and cos Pt minus theta. This is A into omega square minus p square is equal to, we can write this as f cos theta. We will call this as equation 15. And again, comparing the coefficients of cos Pt minus theta, so we can say this is 2b AP is equal to, this becomes f sin theta. We will call it as equation 16. Now, in order to get the amplitude and phase of the forced oscillation, so I have just left this equation 15 and equation 16. Now, in order to do that, what we'll do, we'll square and add equation 15 and 16. So we get a square omega square minus p square whole square plus 2b ap whole square is equal to, this is f square cos square theta plus f square sin square theta. Okay. Now we will simplify this further. So this is a square omega square minus p square whole square plus 4b square a square p square is equal to f square, right, sin square theta plus cos square theta. Now again I will remove the common term here. So common term is a square. So this becomes omega square minus p square whole square plus 4b square p square is equal to, so we know that sin square theta plus cos square theta is 1. So we are left with f square, or we can write a square is equal to f square whole divided by omega square minus p square whole square plus 4b square p square. But we don't want a square, we want the amplitude, which is a. So a is equal to, if we take the square root to the right hand side, so we are left with f whole divided by square root of omega square minus p square whole square plus 4b square p square, where f is equal to f by m. We call it as equation 17. So divide equation 16 by 15. So we get 2b ap is equal to f sin theta divided by a into omega square minus p square divided by f cos theta. So f gets cancelled. So sin theta by cos theta, I will just rearrange it. You can write it as tan theta is equal to 2b ap divided by a into omega square minus p square. Tan theta is equal to 2bp divided by omega square minus p square, or theta is equal to tan inverse of 2bp divided by omega square minus p square. We call this as equation 18. So expression 18 or equation 18 is the phase for the forced oscillation given by theta is equal to tan inverse of 2bp divided by omega square minus p square, where b is the damping coefficient, p is the frequency of the applied force, and omega is the frequency with which the body is oscillating.